So, hello everyone and welcome to the next chapter, and it is going to be the S block elements. So, we have already seen about the periodic table, right? In this particular periodic table, when we are taking a look at it, it is going to be differentiated into different groups. Groups such as the S group, right, or S block, P block, D block and the F block elements. Now, how do we differentiate these particular elements in different groups? It all depends upon the valence shell electrons. Okay, so in this particular case of S block elements, it's actually the valence electron, or we can also call it as a differentiating electrons. Where does our differentiating electron enters into? Whether it is entering into the outermost s orbital, whether it is entering into outermost p orbital, d orbital or f orbital, we classify the elements depending upon that. Okay, so therefore in an s block elements, here the differentiating electrons enters into the outermost s orbital. Okay, so it is entering into the outermost s orbital. Now, due to this, what is going to happen here is these elements are going to be classified as the s block elements. Now, s orbital, we know the capacity of s orbital. It has a capacity to accommodate 2 electrons, right? Therefore, this particular electron, as it has a capacity to accommodate 2 electrons, this entire s block element, we are going to classify it into 2 important groups, and that is called as the group 1 and group 2. Okay, so group 1 and group 2. So, in the entire periodic table, where do we find these S block elements? It is going to be represented in the leftmost corner, and that is the entire section over here. This entire section, as what we see, represents to us the S block elements. Okay, so here, this S block elements are going to be categorized into 2 groups, group 1 and group 2. Okay, we can also call it as group 1A and group 2A respectively. Now, here in the group 1A, the elements that we have are lithium, sodium, potassium, rubidium, cesium and francium. Okay, out of which francium is a radioactive element. So for our studies, we are going to take a look into the group 1 till cesium only. Okay, whatever the properties we are going to discuss, most of the time it is restricted only till cesium. That is from the lithium to cesium. Because of the radioactive nature of francium, we are not going to take it into consideration. Alright? Coming forward with the next, that is the group 2. So in the group 2, the elements that we have are beryllium, magnesium, calcium, strontium, barium and radium. So we have beryllium, magnesium, calcium, strontium, barium and radium. Again, radium radioactive in its nature. Alright, so for today we are going to strictly discuss only with respect to the group 1A. Okay, so that is over here. The elements are lithium, sodium, potassium, rubidium is going to be the cesium. Right? So, here, why do we call this particular group as alkali metals. It is also called as an alkali metals, but why do we call these as alkali metals? Is that whenever we have these elements, and these elements when they are reacting with water, okay, so they form hydroxides on reacting with water. Okay, so as they are forming hydroxides on reaction with water, whatever solution we are going to get are strongly alkaline, or in simple terms they are strongly basic in their nature, due to which we call them as alkali metals. Okay, on the other hand, we have the second group, that is group 2. In this case, what we have is we have beryllium, we have magnesium, we have calcium, followed by we have strontium, right? So finally barium. So in this particular case, these elements on reaction with water, they have capacity to form oxides and hydroxides, due to which we call them as alkaline earth metals. Again, these particular metals or these particular oxides and hydroxides what are formed upon reaction, these are again strongly basic in their characters. So therefore, we call these particular group over here as alkaline earth metals, while these particular group over here as alkali metals. Coming towards the next section to discuss, that is when we take a look into the alkali metals, that is nothing more than the elements of the group 1. Okay, so in this particular case, what happens is we need to take a look into its electronic configuration. Okay, so electronic configuration over here is going to be as the electronic configuration of noble gases followed by NS1. This is for the alkali metals. Okay, while if you take a look into the alkaline earth metals, so in the case of alkaline earth metals, a small change that occurs is because of the s block orbitals or the s orbitals. What happens there is it has a tendency to accept 2 electrons or accommodate 2 electrons. Therefore, it has direct change with respect to electronic configuration, as electronic configuration of the noble gases followed by Ns2. So taking this into consideration, generally the electronic configuration becomes as, for the s block elements, it becomes as noble gases Ns1, 2, 3. Okay, so this would be a general electronic configuration for the s block elements. Now, when we take a look into a bit of more detail, what we understand is that there are elements such as lithium and beryllium. Now, these particular elements, what they do is they show the properties resembling to the other element, especially when we take into the look with respect to lithium. Lithium shows certain properties which are resembling to that of magnesium, while beryllium shows some properties which resemble to that of aluminium. Okay, now this thing happens because of two important factors. The first important factor is because of its ionic size. Because of ionic size, we can say that lithium shows properties similar to that of magnesium, while beryllium shows properties equivalent or similar to that of aluminium. It is because of ionic size, and second one is because of the charge to the radius ratio. Because of this particular ratio, again, lithium tends to show the properties similar to that of magnesium, while beryllium tends to show the properties which are equivalent to that of aluminium, right? And this particular case we call as the diagonal relationship. Okay, so this is the diagonal relationship, right? Whenever we take into consideration of the biological fluids, that is the fluids which are there in the animals, plants, humans, okay, all these particular living organisms, whenever we examine their body fluids, okay, so in that particular case, monovalent ions such as sodium ions, potassium ions, bivalent ions such as the calcium ion and magnesium ions. These particular ions are found to be predominant. They are found largely in biological fluids. So you need to remember these particular cases, that is the monovalent ions such as sodium and potassium ions, while as the bivalent ions such as calcium and magnesium ions. These particular ions are found in the biological fluids. Right, coming forward, in order to take a look into the different types of properties, starting with first one, that is called as the electronic configurations. But this time we are going to strictly discuss this entire phenomena with respect to the group 1. Okay, so in the group 1, when we take a look into the different elements such as what we have is the lithium, right, followed by sodium, potassium, rubidium, cesium. Okay, in this entire case, all these particular elements have one valence electron. Okay, it is going to have one valence electron. That is, these particular metals have a tendency to lose one electron. When they do lose one electron, okay, when they lose one electron, the loss of one electron will result into the formation of ions such as Li plus, sodium plus ion, potassium plus ion. Over here we have rubidium plus ion, of course cesium plus ions, right? Now these particular ions, monovalent ions, are having smaller size when we compare to that of the parent atom, because it has lost the electrons, number of protons have increased, nuclear charges have increased, therefore the size of atom shrinks. Correct? This is what the phenomena occurs. So therefore, all these particular ions which are formed by loss of one electron, we call them as monovalent ions. These are formed by the loss of one electron from the parent atom. Okay, so therefore, what we have to remember here is, in the outermost shell of these elements, there is only one electron which is loosely bonded, and these particular metals have a tendency to lose that one electron and becomes here electropositive in nature. Right? So, coming forward with the second property. And the second property as what we have is the atomic and ionic sizes. Okay, so when we are speaking about the atomic and ionic size, okay, generally in an entire periodic table, as we travel from the left to the right, okay, as we travel from the left to the right in the periodic table, what happens is the atomic size gradually goes on decreasing. Okay, so therefore, can we say that these alkali metals have the largest atomic size in a particular period. So, when we are speaking about a period, in that particular period, what we have is these particular alkali metals are going to have the largest size. And as we travel from the left to the right, the size generally goes on decreasing. Okay, so here, as we travel down a particular group, as we come down a particular group, especially in the S block systems, what will happen is, as we travel from down a group, the atomic size generally increases. Okay, now it increases with respect to atomic size or it increases with respect to the ionic sizes. There is no problem with that. Okay, that is, as we travel from the lithium to cesium. As we travel from the lithium to cesium, this particular size goes on increasing, whether with respect to the atomic size or whether is it with respect to the ionic sizes. This particular size goes on increasing as we travel down a particular group. Correct? To be the ionization enthalpy. So, ionization enthalpy. What exactly is ionization enthalpy? It's nothing more than the amount of energy that we are going to give for a particular atom to remove the outermost electron from that element, provided that element is in its gaseous state. Right? So, applying the same concept in this particular case. So what happens here is, when we take a look into its electronic configuration, it all depends upon the electronic configuration. Because if we take one example and if we discuss, that would be much more easier. Okay, let's discuss taking into consideration of simple sodium. So when we take into consideration of sodium, okay, so here as the atomic number is 11, so what we have is 1s1, so 1s2, 2s2, 2p6, of course 3s1. So can we say that the valence shell has one electron only? As it has only one electron here, okay, let's represent it. This is our first shell. Let's say this is the second shell. And this is the third shell. Okay, so 2 electrons in the first shell. Let's represent this one. 1, 2. Okay. In second shell we have 8 electrons. All right. So 1, 2, 3, 4, 5, 6, 7, and 8. All right. So total so far is 10. of course, the last one is 3s1. So in this particular case, what happens? This outermost electron is perfectly shielded. It's shielded by the help of screening effect. It has been shielded from the nuclear charge. Okay, that means this nucleus is perfectly surrounded by the electrons in all particular directions, and therefore, due to this case, what is going to happen is the effect of this nucleus to the outermost electron has reduced. As it has been reduced, we can easily remove this electron. Correct? So supplying it in a small amount of energy would lead to removal of electrons. Okay, so nothing more than that itself is the ionization enthalpy. Correct? So as this particular electron, we can consider it as loosely bonded. Okay, as it is loosely bonded with that particular atom, because it is perfectly screened, it is perfectly shielded from the nuclear charge, we can remove the outermost electron very easily just by applying some amount of energy. Okay, so when we consider this particular effect and have the same thing over here, what will happen is, as we come down a particular group, the size of atom goes on increasing. As the size goes on increasing, the distance from the nucleus to the outermost electron, that increases, right? So therefore, that last electron will be loosely bonded, or it will be loosely attracted to the nucleus. So as we come down a particular group, small amount of energy would be required in order to remove that electron. So now that means these particular alkali metals have low ionization enthalpy. They have very low ionization enthalpy. And this particular ionization enthalpy, further it decreases. It decreases down the group. That means as we travel from the lithium to cesium, this particular ionization enthalpy goes on decreasing. Okay, so therefore ionization enthalpy is going to decrease as we travel from the lithium to cesium. Coming towards the next property, and the next property is going to be the electropositive nature or the metallic nature. Okay, so when we are dealing with electropositive nature or metallic nature, here it again always goes back to the electronic configuration. As these particular elements, that is the alkali elements or alkali metals, have a tendency to lose one electron. Okay, as it has a tendency to lose one electron, which is again a nature of metals, it easily generates a monovalent ion. Okay, it easily generates this monovalent atom. Therefore, due to this, it is going to have a metallic nature. Secondly, these particular alkali metals are very good conductors of heat and electricity. Okay, the important factor here about any metal is its lustrous nature. Lustrous nature, in a sense, it is the shining nature of any metal. Okay, and in this particular case, the lustrous nature in alkali metals, in this alkali metals, is all because of free electrons. Now, what exactly these free electrons are going to do is nothing more than because of It is because of the oscillations of these free electron, the one last electron which is present in the valence shell. It is all because of that what we have is the lustrous nature of these particular metals. Okay, so therefore the electropositivity or the electropositive nature of this particular alkali metal is because it has a tendency to lose an electron in order to form a monovalent ions. Okay, these are very good conductors of the heat and electricity. Important factor is its lustrous nature or lustrous or shining appearances. Now this shining appearances is because of the oscillation of the free electrons which are present in the metals. Okay, followed by, now we shall continue with the next one, and that is going to be the hydration enthalpy. So, hydration enthalpy in a sense, how much amount of energy is released when one molecule of water combines with one molecule of these particular elements. Okay, so therefore, hydration enthalpy in this particular case is actually low. And these particular hydration enthalpy goes on decreasing. It goes on decreasing as we travel from the top to the bottom. Okay, it is from the lithium ion to sodium ion to potassium ion, followed by rubidium ion and cesium ion. As we go from the top to the bottom, the enthalpy or the hydration enthalpy goes on decreasing. That is, how much amount of energy is going to be released when one molecule of these particular ions are going to combine with one molecule of water. Okay, and that is where, if we observe this entire trend, it is the lithium ions which are having the maximum hydration enthalpy. Okay, it is the only one which has the maximum hydration enthalpy. Coming forward with the next one, and that is going to be the physical properties. So when we are taking a look into the physical properties, let's start with the physical appearances. Okay, so in the physical appearance, first thing that we have to understand, in the physical appearances we have to understand that all these particular set of alkali metals, they all have silver white in color. Okay, their appearances are silver white in color. Okay, so therefore, first thing is they are going to appear as silvery white in color. Okay, secondly, when we take a look into them, we find that these are very soft metals. Okay, now because of their large size of atoms, atomic sizes which are very large, therefore they have direct impact on their densities. Thus, these particular metals have low density. Okay, and this particular density goes on increasing down a particular group. That is, as we go from the lithium to cesium, the density goes on increasing. But potassium has lower density when we compare to that of sodium. And next important thing that we have to remember is the lithium is the element or the metal with low density. Okay, so these are the important points what we have to remember about the alkali metals' physical properties. Moving forward with one more important thing. Okay, when we take a look into its boiling point and melting point, what we find is the boiling and melting points for alkali metals are quite very low. Now, why it is low, or what does it indicate, is that between these particular elements, whenever we have the sodium metals taken, okay, between the atoms of sodium, whatever the bonding, the metallic bonding we have, okay, those particular metallic bonding in all these elements are very weak. So therefore, this particular thing indicates that there is low or less metallic bonding. That is, the bonding between different atoms are very less. Okay, so therefore this is an indication right from the low melting point and low boiling point. Okay, now when we subject these particular elements to flame, okay, all these particular elements will exhibit different type of color. Now, why is it going to exhibit different type of color is because whenever we have an atom, now this particular atom will be having numerous number of orbit, right? Now, in the orbit, what will happen is the last electron, let's say we have one last electron over here, let's say this is lithium into consideration, and as we supply in the heat energy to this particular lithium, what is going to happen is the outermost electron is going to absorb that energy and gets excited. Okay, now as it gets excited, it reaches to certain orbit, comes over there, rests for a while, and further it is going to de-excite. The moment it de-excites from a higher energy level to the lower energy level, it will start radiating the radiations. It will start giving out the radiations. And these radiations which are coming out, it falls in the visible region. As it falls in the visible region, we can see different color for different element. Okay, so therefore, the main cause of the occurrence of different colors when we expose these particular elements to flame is because that the excitation and the de-excitation of electrons which are involved, especially the electron which is present in the valence shell. Okay, so therefore, when we take a look into elements such as lithium, sodium, potassium, rubidium, cesium. Okay, so when we have any particular salt of lithium and that we are going to put it in flame, okay, that time the color of flame changes to the crimson red color. Okay, when we have sodium salt and when we put the sodium salt into the oxidizing flame, we get a golden yellow color. Okay, followed by when we have potassium. This potassium type of salts will give us pale violet color, while rubidium and cesium salts give us violet color flames. Okay, and this is what goes true from these particular elements. Alright, so here we end with the physical properties of the alkali metals. In the next video, we will be observing about the chemical properties, chemical reactions of these alkali metals. Right?